Okay, I want to tell you about conductors that are in electrostatic equilibrium. Okay, first of all, what is a conductor? A conductor is any material that will allow electrons to flow through it very easily. Okay, it's materials where the valence electrons they are free to roam around in the material. So usually we're talking about metals in this case. Okay, and what we mean by electrostatic equilibrium is if they're charged, the charge is done moving around and it's stationary. So the charge is done moving and it's no longer moving. So I want to tell you about conductors, metals, in which all the charges are stationary. Okay, so here's something that is going to become pretty important, and that is that any conductor that is in electrostatic equilibrium will have no electric field inside of it. So any conductor that is in electrostatic equilibrium will have no electric field inside. Say that one more time. You see this? Let's say it's a big hunk of copper. So if this is a metal, and if it's in electrostatic equilibrium, meaning the charges aren't moving, then the electric field inside of it will equal 0. And here's why. If there was a field inside of it, if you do put a field in there, there's charges in there that are free to roam, and so they will. So if you put a field in there, if there is a field in there, the charges will move, because that's what moves charges. What moves charges? Electric field. So if you look at a metal and you see all the charges stationary, you go, hey, there must not be a field in there anymore. What will happen is if you put a field in there, the charges will move around until there's no more field in there. Okay, so if this is a metal and if it's an electrostatic equilibrium, then E equals 0, because if E did not equal 0, the charges would be moving. And if the charges are moving, then that's not electrostatic equilibrium. Okay? All right, so let's take a metal sphere, a metal sphere, and we'll charge it up, put a bunch charge on it. I want to show you something. So we charge it up. We'll charge it up to charge Q. Okay? I want to convince you that the charges are going to all hang out on the edges. I want to convince you that the charges won't. This is a solid metal sphere. This isn't a hollow metal sphere. This is like this big chunk of metal. But when I charge it, the charges will all end up on the edges. Okay? And the reason for that, if it's metal, the reason that I'm going to give you is Gauss's law. Okay? So I'm going to ask you, is this charged? You're going to say, yeah, it's charged Q. And then I'll say, is it in equilibrium? And you'll say, well, it's been sitting there for a few seconds. And I'll say, oh, then it's in equilibrium, because it gets equilibrium in like nanoseconds or even more, because electrons move very fast. So if you say it's been sitting there for a while, I'd say, oh, okay, well, then it's probably in equilibrium. Okay, so if it's in equilibrium, then the E in here has to be 0. Now watch. If I make a Gaussian surface right here, if I make it almost the size of the sphere, then the E right here has to be 0, because you're inside the metal. The E in there is 0. So Q enclosed over epsilon naught, the net charge enclosed, I should say the net charge enclosed, over epsilon naught is equal to the integral, the closed surface integral of E dot dA. Okay, well, let me tell you, if there's no E there, or there, or there, or there. You know how much flux is going through the surface if there's no E at the surface? Well, by golly, there's no flux going through. If E is 0, this whole thing turns into 0. So you know what the charge has to equal? The charge enclosed? The total charge enclosed must equal 0. And so, like, if I look at all this charge in here, enclosed, it's 0. So where is this charge hanging out? Right here. Right on the surface. Okay. Now, let me go a little further with a metal sphere then. So I charge up the metal sphere. And I want to find out what the electric field is outside of a metal sphere of radius r. Okay, well, let's say right here. I want to know what the field is right there. So what I'm going to do is I'm going to put in a Gaussian surface. I always dot my Gaussian surfaces to remind me that those are imaginary. And I just say the charge enclosed. Wow, that's a weird cue. The charge enclosed, the net charge enclosed, over epsilon naught is equal to the closed loop surface integral of E dot dA. That's the net flux through the surface. That's the net flux through the surface. And I'm thinking that the charge enclosed is, if this is charged up Q, then the charge enclosed is just Q over epsilon naught. Okay, now would you agree that for my Gaussian surface, the dAs are this way? They're normally outward or perpendicularly outward. And so is E. E is this way too, if that's positive charge. So if that's the case, then I can get rid of the dot product. So gone is the dot product. Because E is parallel to dA, so you can get rid of the dot part of the dot product. And now E is the same at every point on here, so I'm going to do this. I pulled that out because E is uniform for all points on the Gaussian surface. And then when I add up all the dAs, I just get the surface area of a sphere. Little r squared. You're out there a distance, little r squared. All right. So now let's solve for the electric field. And if I do that, the electric field, let's put it over here and solve for it. The electric field apparently is going to be Q over 4 pi epsilon naught r squared. Hey, that's the same. That's outside of a sphere, and that's the same as k q over r squared, because 1 over 4 pi epsilon naught is equal to k. Okay, so if I were to graph the electric field for a sphere as you head out, it looks like this. Up to the radius r, it's 0. And then once you get to r, that should be dotted. That line should be dotted, and then it comes down like that. So that's the electric field for a solid sphere. All right, thanks. Bye.